So my name is Paul Prenny. I'm situated in the University of Windsor. I'm one of the SharkNet representatives, and today I'm going to be talking about profiling your program. So basically, I'm going to start right from the basics and go up. I'm just going to show you a few slides first, but then I'm going to just present uh, the thing so you can see how it's done, because even the simplest things are some of the most commonly asked questions that people want to do. And so we're going to do with some of the simple things first, and then I'm going to show you fancier stuff as we go on. This talk could easily become several talks, but I'm going to start from the basics today. So profiling. So you want to profile your code and you figure out what's going on. Why do you want to do that? Well, you want to know how much time the program needs, how much memory it needs, and all of this stuff, because maybe it's too much or this or that, or maybe you can make a tweak, make your jobs run faster or whatever, or anything. You have a reason to look at your program and you want to get some information out of it. Okay, so well, first of all, what is profiling? Profiling is measuring metrics about how your program runs. Very importantly, how it runs. It's not analyzing source code and telling you stuff. It is how your program runs. In fact, you can profile any program that runs on the computer. Mind you, if there's no debug information, it won't be very useful because everything will be spit out stats in terms of assembler instructions and all that, but maybe that's what you want, fine. However, in most cases, you want to profile code that you have source code for. And so I'm going to talk about that. There's a couple important points, but when you measure stuff, when you profile your code, you're doing it for how much RAM you're using. Sometimes it's over time. Sometimes you want to just know execution time. Okay, that's a very simple aspect of it. But sometimes you want to know how long it takes it's spending in a particular subroutine in your program. And if it's way too much, then there's something you got to do about it. Obviously, some obvious points. If your program starts in main and it ends when main ends, then your program main will run for the whole program. So that's moot. We're not talking about that. We're talking about some function call that you make in your program. Is it spending way too much time there? That's the kind of thing you can use a profiler to figure out. Instruction use, or if you have source code and debug information there, you can see that map to what your source code is. Okay, there's also a need to profile code to aid program optimization. I'm not going to talk about that today, but most compilers have features that if you compile them with a special feature, and then you run the program once, some of them let you run it more than once, it records some data, and then you compile it one last time. And then it will optimize the code based on what the compiler was profiling. To do this, you need exemplar input data. Your program should run quicker than a normal job run, but it will optimize things so that your code will run faster. So that is another very useful need for profiling. Okay, but very importantly, that note there, it doesn't analyze your source code. It merely looks at the running program and samples it. It says, where are you now? Where are you now? Where are you now? Where are you now? And things like that. And then it just records that and it maps where are you now to the debug information. And if you don't have any debug information, then the binary assembler information of your code. Okay, and then it saves it all in the file, and then you can view it in various ways. So if you're doing the hardcore profiling, that's what it's all about. Okay, but so that's fine. Now I mentioned about profiling. When you profile your code with a profiling tool like vTune or perf or any tool that does profiling, you need to have debug information, because usually this is code you've written, I assume, and you want to see stuff mapped to the programming language you wrote it in. And if you don't have debug information in your code, you won't see it. You'll see binary addresses and basically assembler. Most tools will show you the disassembly of the binary assembler, but unless you know assembler or something about your machine architecture, that might as well be in a language you don't speak. Okay, so how do you prep your code? So I'm going to be demoing this after I show you initially how you can get some very simple raw time, how long your program runs, and how much memory your program uses. There's some very useful tools that often get overlooked. I'm going to show you those first. But then if we're going to compile with debug information, and then you're doing your job run, here's the dilemma. You're doing your job run, you got it working, great. Now you want it to run fast. So you compile your code with all the debug all the optimizations. You typically turn off debug information and things like that. So what do? Well, you want your optimization. So put your -0, 1, 2, 3, whatever you need for your code on the compiler option. Say, I want the optimizations, but very importantly, also put -G3 or GDB3, turn on the debug information. And you'll say, wait a minute, that means the debug information goes into my program, right? Yes, it does. And if you don't do anything else, that's not a good thing. That will affect the performance of your program. Okay, but these additional bullets here, if you do them, it will separate from your program the debug information and put it in a separate file. So this extract debug information line in this bullet here, object copy, keep only debug. You tell it your program name, whatever you saved it as, and then you give a name where you want a file you want to throw all the debug information. Doesn't matter what you call it. I just called it this, so it makes sense when I do an ls. Okay, .debug info. There's my debug information. And then what you do is you strip the debug information from your executable. Okay, this is true no matter if you're using the Intel compiler, the NVIDIA compiler, the GCC compiler, whatever, this is what you would do. When I mention the NVIDIA compiler, I'm talking about CPU only right now. This will not profile your GPU code. So follow the instructions for NVIDIA if you're doing stuff on the GPU. But if you're on the CPU, this will work. Object copy and strip are commands that come with the Linux operating system. If you have certain packages installed, not a problem. They're there for everyone. So you want to keep the debug information. You basically copy it all in a new file. Then you strip it from your executable, which will make your executable much smaller. Okay, actually the final size will be, if you always run strip, it'll be the final size of your executable when you compile with optimizations and no debug. So, and then you do one extra special command. You use the object copy command to tell the executable, okay, that the debug information is in the file you did on this first object copy command. That way, when you run a debugger, so we're not talking about debugging today, but if you run a debugger or you run any tools that need to use that debug information, they know where to find it because you told it what file it was in. So you have to add these 3 extra commands and remember to compile your code with debug. The final output of your executable after you strip it is just like your optimized code. Fabulous. But of course, you don't and you want to run with optimized codes typically because you want to see how fast things run with your optimized code, not your unoptimized code. Great. Okay. But you need that debug information if you want your tool to map things back to your source code. One word of warning. With optimizations, if you've ever used a debugger, you know that with the debugger, you can jump all over the place with optimizations. That's still a reality, but you still want to get mappings to your source code optimized, because the idea of profiling your code is how fast is my code running, where is it spending its time, and you want to find out that for the optimized version of what you're running on our clusters. You typically don't want to find out that in general with unoptimized code. Obviously, you're the judge of that, and if you don't want to have optimizations, then turn that off, but I'm just letting you know this works when you do it even with optimizations. So that's kind of nice. Okay, so you're on the cluster. So I'm on Graham right now. Okay, you're on the cluster and you say, hey, I want to do some things, right? Okay, so we got some code here. Okay, now I have programs here that run relatively quickly. But first of all, one of the most common questions people ask is, how much memory does my program use? And on all of our cluster there's a utility called memusage. Okay, and I'm going to demo it here from first principles so you can see how to go about doing it. If you don't remember anything in your head other than memusage, okay, where do you start? Well, okay, you're logged in the cluster. Well, what you can do is go man space. So man is the command to give you help information on various commands and function calls and stuff like that. So if you type man space memusage, and we hit enter, it's going to give you a nice page. Okay, and immediately you're going to see, oh, it's a bash script which profiles memory usage of the program. Great. Program is what you pass to it. Okay, that sounds pretty good. Mem usage summary, hey, we get the total. Heap is just how much memory you're using, but it also tells us about how much stack space we're using. So if you've ever blown your stack or your program has heavy recursion in it, then that's what this is. So we can just use it. Okay, how do we use it? Well, we can put, first of all, you say, hey, I don't know if I have a program to use or whatever. Well, let me point out something. If you scroll down, let's say there's too much reading, too long didn't read. You saw you could use it. Okay, let's go down here to the bottom. Hey, right at the end, there's this example, and it's showing us how we can use it. Great. Okay, we scroll down a little bit more. It even gives us a sample program. So if you just copy and paste this code out, it's C code, no problem. We can do it. So I did that already. Okay, so I will show you. Prog.c is just that program. I didn't even bother removing the indents. I just copied it straight out and put it in this file. No problem. So if you do that, okay, let's not even worry about how we're compiling it. It's just C code. We just do this, boom. Okay, now we get a dot out. Okay, now one reason why I'm doing this is someone else's program. Yes, it runs really fast, but you might say, how long does this program take to run? Okay, well, you can type time, but that won't give you what you really would like to see. What you'd rather do is you put user slash user slash bin slash time, write it that way. Okay, and if you want the output to be nice, human readable, that you don't have to be an expert on, just put -v. I'll show you it without -v in a moment. Okay, now we want to run our program. So whatever command you use to run your program, put it after the time command. Just put it there. So in this case, we want to run a dot out. Okay, so now when I hit enter here, there we go. Okay, the program spits out some information here. Anything your program spits out, it will. But the time command, just when the program quits, so the program has to run and quit. The time command will give you a bunch of information, and -v puts English out so you can figure out what's going on. Okay, and what you want to pay attention to is the maximum residence size. Okay, and the elapsed wall clock time in seconds. This ran so fast it's 0. Okay, but your programs, probably don't run so fast as 0 time. Well, you will see a meaningful wall clock time here, and when you need to know how much to tell Slurm, maybe you have an input data set that runs quicker, but you can extrapolate to how long your job will run. You can use this elapsed wall clock time to do that extrapolation. Obviously, you don't want to do this with your real job, running real data. That would take way too long, because then you'd have to put way too long of an estimate. If you don't know how long your program runs, that's an issue. Now, what I see a lot of chemists do and other researchers do, including you can use this with any program. You can time any program. So what you do is you give it input data. Obviously, it'll run quicker, but maybe if you're a chemist and you do one molecule, you can multiply, hey, if I do this with 150 molecules, this is how long it is. And you find out how long it takes for one, and you multiply by 150 and then add a little extra because you don't want the scheduler killing your job, that kind of thing. Okay, so that's how you can find out how long does the program run. Now, if you don't run it with -v, it gives you more terse output. So let me clear the screen here. So you can see it. This program spits out all kinds of realloc lines, but you can see it just crams all that data into 2 lines. And the elapsed time is the elapsed time. This max resident thing here, and it's saying it's in K, is how much total RAM it used. But there's a nicer tool to use called mem usage. So I'm going to show you that in a minute. But if you need to estimate how long your program runs, use the time command, run it with a smaller input thing because you don't want to take 3 weeks to run, and get some numbers that you can extrapolate out and guesstimate how long your full job will take, and that helps you there. Next step, how much memory does the program use? So if you just go mem usage a.out, so it's just like the time command, user bin time space, you can go a.out. Well, you just go mem usage a.out, no modules to load or anything, and you can do it with any program. When you do that, okay, your program's going to still spit out its output. That's what happens with these tools. They run your program for real. Okay, so you do it with your exemplar data set that doesn't take as long to run again because you just want to get some numbers, but you can figure out stuff. Oh, it uses this much RAM for whatever that input is. And then you can, maybe that's all the RAM you need, but in many cases you extrapolate that and say, okay, this is the total amount of RAM I need. Now, if you just run mem usage and nothing else, it gives you a text screen dump of what you use in your code. Okay, so that's good because it'll give you some numbers. For example, mem usage summary. Okay, so it's given us some numbers here. Great. Okay, there's no units, they're in bytes. And it will tell you the number of calls to malloc, realloc, calloc free. Most won't worry about that. Okay, most of you will just care about the total heap. Okay, and some of you, if you have heavy recursion, will care about the stack peak, and it will give you what's a text screen histogram, equal signs. Okay, and you can see memory going up and down. Now that looks okay, but text screen output might not be what you want. Can you do better with this command? Actually, you can. In the man page for it, actually, I'll just bring it up again. Mem usage. Okay, so you got the descriptions of blah, 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 blah. Let's go down to this example. Okay, look what we have here, dash data and some data file. So we can write a data file. That's pretty cool. And look down here, mem usage stat, which is another command. It's in the same package. You don't have to worry. You can just go mem usage stat. You can take that data file and make a bitmap PNG file. So let's do that. Okay, so I'll put dash and put some data file. We'll run the same thing, and then I'll convert it to a bitmap. Okay, and you might like the output. Okay, so we do this. Okay, the code's compiled. I got a.out. Great. Mem usage dash data. Okay. How about mem.dat? Okay. Give it some meaningful name. Doesn't matter what the extension is. And we'll just run the program. There we go. Okay. When it runs fast, boom. If it doesn't run fast, your program would output stuff or whatever. And then when you're done, you're done. So you get this output and you think, oh, what's there? But if you do an ls now, you can see there's a mem.dat file. Okay, so mem usage stat. Okay, and it was mem.dat. And how about mem.png? It only does PNG files. So mem.png, we do this. Okay, now I'm logged on the cluster. with SSH. I have no graphics output. How do I view this? I need to transfer it to my own computer. Okay, so the way you can do that is this. Okay, if you type pwd enter, that will tell you where you are on the computer. Okay, now realistically, if you're running these things and doing these profiling and all that, right now I'm on the login node because these run blazingly fast in a blip. Okay, but if you're doing anything serious, you want to be on the use salloc and go on a compute node. This will still work. You run pwd, you just type this to get the directory you're in your disk space, and then you open up another window. So here, okay, and how about we go to, I'll just make a silly directory called Q. All I have to do now is transfer that file. So if I go SCP, and I got to put what my login is at the cluster, okay, and then I can paste that pwd thing. So just paste the output there, and then it was mem.png. So if I type all that, I'm good. I need to put space and a dot at the end. When you hit enter, it will ask you for a password unless you're already connected with SSH in some cases. Type in your password and it will copy that file to your computer. And the end result is you will have the file on your computer, and then you can run any program that can view it or open up a graphical display of your files on your computer, and you can double click on it. And of course, it's a bitmap, and you can open it up, and this is what you'll see. So this is why their demonstration program is nice, because they constantly allocate and reallocate memory. So it jumps up and down, and you can see this very nicely. Now, what is this showing me? On the right-hand side in green is the use stack space. So we only use 2K of stacks, so that's good. And we've got plenty of stack space. But if your program is heavily recursive, you'll see this green line go up and down. Okay, or if it goes very deep into function calls, you'll use a lot of stack space with it, it'll go up and down. On the left axis, and the stuff appearing in red, is the amount of allocated memory, and the units will scale to whatever your program uses, into the gigabytes and all that stuff. So you can see the allocated memory goes up and down. Okay, now at the bottom here, it says memory handling function calls. This is not really time, it's in terms of function calls in your program. So over the execution of the whole program, okay, this is how the memory went up and down with each function call. Okay, there weren't too many function calls here. It says 43, but that's what it shows. Now you'll say, okay, but you want to see time. How can you see time? Well, mem usage stat, we do that. And if we look right here, -t time, use time rather than the number of function calls as the scale for the x-axis. I did that on my computer, but it's the same thing on the cluster. Okay, there we go. Use time as the scale for the x-axis. Okay, and you can even have a graph of total memory consumption. So there's some things here, and some of you might want larger bitmaps. You can go -x-y and get them. Okay, so what I'm going to do is tell it to regenerate that bitmap for time. Okay, so mem usage stat, hit the up arrow a few times, -t. Okay, let's do the same thing. It'll run really quick. Now I'm going to transfer it to my computer. So hit the up arrow. There's that command again. There we go. Okay, if you have mem usage stat on your computer, you can just download the data file on and run mem usage stat. If we do this, there we go. So notice at the bottom it says memory handling function calls over time. Okay, so this gives you an idea of what happens over time. Now, this program ran so fast, you see little artifacts like this, but normally programs run and they set up and they use a fair bit of things and then they do their thing. So you'll see the flow of your program in terms of how much stack space you need and how much RAM you need. Now, to submit a job, you tell it the total amount of RAM. You inflate it a little bit, of course, but you tell it the total amount of RAM. But you might want to know how your job uses RAM over time. And nicely, you also get this from it. If you just need to know the total amount, you can look at the text output. It tells you heat total. That's how much, or that's the max resident size when you run the time command. Okay, so these are two really useful commands, and they'll get you going on where do you start in your code. And nicely, they do not time hard, not at all. This command, the memory one to do things while your program runs, does have a tiny bit of overhead, but it won't appreciably increase the time your program takes to run or the amount of memory it uses. So that's another reason to use these two particular tools, is you can run them, get a very good idea of how much time and memory you're using. Mem usage stat does not tell you the total time though, just plots it over time if you want that, but it can very certainly tell you how much memory your program used. You may need to inflate it if you're using external libraries and things like that, but it gets everyone started. Fabulous. You can run those two commands on any command that you can run on the computer. So if you want to run it on ls, let's say you don't have a program yet and you just want to get how much memory ls is using, then you would just go here on the cluster again. You can just go mem usage and you can type ls. I'll just ls in this directory, or ls-l, doesn't matter. You can do that, okay? And it gave me mem usage. That didn't give me the total memory usage. I don't know why, but whatever, you can run it on other commands. Okay, so great, you got that. Now, you might say, I want more information from my code. Great, more information. Okay, so let's take this program I have here. I've already compiled it. So when I compiled it, I made these exe files, and you can see these debug info files. And what I want to point out to the debug info file, I generated them just like the same commands I mentioned on my slide at the beginning. This here is a big file. Now, if you don't like seeing the number of bytes, we'll put ls-lh. H will summarize the number of bytes into units for human consumption. Okay, and just give us the thing. So the debug information here in this program is 393K, right? The executable is only 19K, okay? Now, the reason I'm mentioning this is if you have a larger program, you can expect your debug information to be quite large. And if you compiled with -G3, to get the debug information, that writes the most debug information. And if you find the files are too big for your taste, or it's too much, or it has information you don't care about, it's just too much information, you can reduce the file size by dropping the number. So if you go -G and you put a 3, that'll give you the most. Generally, the 3 is the highest. But if you go 2, it'll give you less. Don't go below 1 though. 1 is just like line numbers and some really basic information. But your debug file size will drop when you do that. And you always generate the debug information when you compile your code. So if you want to change that, you need to recompile your code. Okay. So actually, let me just demo. If I compile the code here, okay, and this is C++ 14 code, but it doesn't matter. It could be C, C++, whatever. Fortran. Okay, so I want to compile my code. I can't just put, I need to put options like I need. I said, this is C++ 14 code, so I got to put that. Okay, no choice there. If I want to optimize, I can put optimizing. If I don't want to optimize, I can say 0 if I want. That's okay. Okay, if that's what makes sense for you, great. But I do want to put in how much debug information. So you can go -G and then put a number, and that'll work with all the compilers on our system. But with GCC, you can go GDB and it will give information that's ideal for GDB, the GNU debugger. So if you're debugging your code with GDB or any tool that uses GDB, you'll get better results with the GCC compiler if you put -G for the debug, and then say GDB, and then put a number, 1, 2, or 3. Okay, so if I put the number 2, for example, okay, here, and now if I go ls-lh, okay, it wrote a.out, and notice that's my program is 143K, you know, pretty large. Okay, so then how do I extract it? I go object copy only. These are on my slides at the beginning, so if you're looking at this later, you can go back to the beginning of the presentation. So I go only keep debug, I give the program name, and then to avoid confusing myself, let's call it a.out.debuginfo. Okay, I'm just making up that extension. You can give it whatever you want, but you don't want to say, what's this file for later? So it's probably a good idea to do that. So if we do that, now we go ls-lh, you can see I got the debug information here. So 124K of that 143K was debug information. Okay. Now I want to remove the debug information from my executable, because if you compile with any optimizations at all, the debug information adds so much junk, that's debug junk, that if you're not debugging your code, you don't need it, but it can affect some of the program performance. So what you want to do is remove the debug information. So you go strip debug and strip unneeded. And this says to remove all the debug information and anything else that's not needed in the program. Okay, because it leads a lot of junk. Okay, and you pass the name of your program. So we do this, boom. So now if we go ls-lh, you can see this program now is 23K. Okay, that's good. That's much smaller. Okay, this here was compiled with more settings earlier, but 23K, and also, well, it's 23K, and that's good because this is on par with stuff. Because what I like is I like to profile my optimized code, and then the executable that's optimized because there's no debug information in it, I can run as my job. I don't have to recompile it. So that's the other thing I like, is that I have the final product I want to run, and I want to profile that. So your last step, though, before you use any tools like the debugger or profiler, you need to run object copy one more time. And this time, you need to go add GNU debug link, and this will work for the other things. If you're using Linux, it'll be the add GNU debug link thing. Okay, and then a.out.debuginfo, you want your debug information first. That is what you're linking to. Okay, and then you want the name of your program, a.out. This adds a special section to the executable code so that a debugger and profiler knows where you put the debug information. And if we go ls-lh, you'll see that it would have increased by a few bytes the size of your executable. So you won't see a change if you use the H option. But this debug information now is linked to it. So what does that mean? Well, it means if you run GDB, okay, and on the executable, so you do that, okay, and you put break main, this is a C++ program or a C program, you can go break main. Look at this, breakpoint 1 on this program, line 21, it knows about it. Fabulous. Okay, so you can debug your program. You can go stop. Oh, I got to run it first. So run, there we go, step, there we go, line 4, it knows we're at line 4. Awesome. Okay, so that's why this is good, because now you can print out variable names. You know, it's saying class Ackerman and this and that and whatever the code's there. That's because the debug information is in it. Now, the purpose here is not showing you how to use a debugger, so I'm going to get out of there. But you can see it works with the debugger. That's pretty nice. Okay. Now, you can run the program directly. Okay, so if I run this a.out, you can see it runs, and it spends some time there at the end. I Control-C it, and you'll say, well, how much memory does this take? You can go mem usage, okay, and you can say a.out, okay, it's going to run your program, and it's going to output stuff. Great. So you didn't know what this program was. Your fellow researcher gave it to you and said, you got to run this. And you say, oh, and your fellow researcher said, I don't know how much memory it takes. Okay, well, just run mem usage. Look what we got here. We got a number. Now it's in bytes, so we need to divide. Now, if we look here, we got 36 million here. Okay, so 36 megabytes. Okay, so it doesn't seem to use too much. Fair enough. You can also run the time command. So let's say you need to figure out how long it takes because this pretend was with sample input. Okay, well, how long did we spend running it? So user bin time. I'm going to put -v because the output's nicer. Okay, I can read it. There we go. If you like short output, then don't put the -v, but I'm going to do that. So it's going to run. Okay, and then it's going to tell me, okay, this is a serial program. It doesn't do it in parallel. Percent of CPU, 99%. Great. Okay, if your program does a lot of disk I/O and things like that, and certainly if you do things in parallel, you'll see differing numbers here. But typically, it'll be 100% on a serial program. And the elapsed wall clock time, 2.6 seconds. Great. So this is what you want to see. 2.6 seconds that took. Awesome. Okay. Average resident set size. You'll see kilobytes. Okay, so kilos 1,000. So here, what, 61.9 megabytes? Okay, this number is higher because remember you have to include all the libraries used and stuff. The mem usage command tells you how much memory your program uses. The maximum resident set size when you run time tells you how much memory the program uses, including all the libraries. So you need to use the bigger number when you do your job things. That said, most of your jobs that people are running on our clusters use so much memory that the amount that the libraries use is insignificant usually compared to it. So mem usage winds up being really nice. Okay, so now we got this. You'll say, wouldn't it be nice to see a mem usage plot? And then I'm going to start talking about profiling. But if we go mem usage, okay, we'll do it on a.out. Oh, wait, we need the -- data. Okay, and we'll call it mem.dat just because that is easy enough to remember. So we do that. Okay, it's going to record some data. And you can see here, the histogram is big and then it's small in two little chunks. Okay, fair enough. Then we go mem usage. Okay, we want that time thing. We'll see it over time. And mem usage dat or memdat to mem.png. I'm in a different directory now. I'm in the Ackerman directory. Okay. And did I call it memdat? Do I have anything in here? I got memdat. There I go. Mem usage stat. There we go. Mem usage stat. -t memdat mem.png. Hit enter on it. Notice the memory stats. If there's a lot of memory activity in your program, that can get the file can get rather large, but large is all relative, and compared to most research data sets, it's not large at all. Okay, so now I got that file. So I need to get this on my computer, pwd. If you are on GravEDI or you're using Jupyter Hub on the cluster, you can run these commands inside of Jupyter Hub, and you can open up the desktop window in Jupyter Hub, or GravEDI is already graphical, and you can just open up your file view and double click on it and view the bitmap. But we don't have it on. We're using text SSH. How do you do it? Transfer that to your computer. So that I type pwd, and that's where I'm at. Okay. So now I'm going to, let's remove the file I had here so we don't confuse the old one. Okay, so now if I go SCP, you put your login, and then you put the cluster you're logged in on, and then you paste that thing there and put the file name mem.png space period. Period is the current directory. So if you want a different spot, replace period with where you want it. Then you hit enter. Okay. Might ask you for your password. Great. If you do that, enter your password, but then we can view this mem.png. There we go. Well, that's interesting. So you can see in spurts, it winds up allocating a bigger chunk. So without even looking at the code, we can see over time, this program allocates bigger chunks and then doesn't need them and then allocates them and frees them and allocates and frees them. Okay, that's interesting. And also you can see I use a lot of stack space. Okay, so this just goes way up there and you can see how it's done. So if you know something about the program, that's kind of nice. And you can see this is the memory use over time. Now, in some programs, maybe this kind of usage is bad. Maybe you say we shouldn't be going to 0. We should just kind of gradually increase and stuff. And maybe you need to investigate that. Fair enough. But that's the advantage of seeing a graph. Okay, so you got that. Great. Now what can you do? Well, there are some other commands you use. Okay. So here we have the a.out code. Okay, so we're using this. I won't bother with the other things here. It's the same thing, just compiled slightly differently. Okay, so I want to get some more performance stats. Okay. Now, there's a program called perf on our cluster. There's also a program called vtune. I'm not going to talk about that today, but vtune is from Intel. And you can use it on our cluster as well as text, and it produces reports and different kinds of reports. And sometimes some people find vtune more useful for its reports. And vtune's really useful if you use the Intel compiler, but you can use other compilers. If you compiled with other compilers, you can still use vtune. It just might not output as nice information in all cases. Now, perf is a command that's already installed on our cluster, so you can just run it. You don't have to do any module loads. Now, if you go perf stat, okay, and you do nothing else, just perf stat and the name of the program, like this. Okay, let me clear my screen. So perf stat and the name of the program. Okay, now I'm going to hit enter. Okay, so you're going to see your program output happen, and then it's going to spit out some statistics. And it's going to be, okay, that's interesting. Perfstat has a nice feature that you can add -d, and every time you do, it'll add more information in the output. So let's do it 3 times. You don't want to go more than 3 because you'll see it doesn't output anything more useful. But if we go -d 3 times and we run it, okay, you'll see it outputs even more information. Interesting. Okay, so what are the things being output here? Well, let's get an idea of some of this. Okay, task clock. Oh, wait a minute. That's how long my program took, but it tells me in milliseconds. And it also says the percentage of use of your CPUs. So if there's more than one CPU being used, you'll see numbers that are relevant. This program is much smarter than time. Okay, it does more tracking of things. Okay, and it has some values you might see not supported on some of them. Don't panic on that. There's nothing to worry about. Okay, and it has some values, and hopefully you don't see any CPU migrations, and hopefully there's no real context switches in your code. If you think they might be a problem, you can submit a ticket, ask for help. Generally speaking, you have no control over these because that's how the system's running. Okay, now you may see CPU context switches and migrations if you have whole node allocation and you have the whole node to yourself and you don't do anything to lock parts of your program to certain CPU sockets or cores or whatever. Okay, you can see that even without whole node allocation, but if you're running a serial job, Slurm will fix your job to 1 CPU. It won't change it. So you're given that job and it'll fix it to 1 CPU. So the only way you can see some of these things is you'd have to have a parallel programming and you're asking for more than 1 CPU on 1 machine. Otherwise, those will wind up being 0. page faults are important. Page faults happen when you access memory and it's not in the cache. I'll put it that way. So when you access memory on your computer, your CPU does not, the CPU core you're using does not directly access memory. The CPU core says to the virtual memory manager, which most modern machines have that, says to the virtual memory manager, I want to access this. And the virtual memory manager sees is it in the cache right now. So when you buy a computer, all of them, in the fine detail, it says, oh, there's an L1, L2, L3 cache, and this is how much memory there is and all that stuff. Well, so that's what happens. The virtual memory manager says, is this already in the cache? If it is, it tells the CPU where it is. Okay. If it isn't, the virtual memory manager goes out to memory. So it's sort of like going to the library. You have somebody to help you, and you say, I need this. And that person helping you will look for it. If it's here, then they'll give it to you. It's right here. Here it is. Okay. But if it's not there, they go running out to the library. You sit and wait. They go running out to the library. They find it. Okay. And then they bring it back and they give it to you. Well, that bringing back and giving it to you is it goes out to main memory, gets the information, copies it to the cache. Okay. And then you're told where it is. So the CPU talks to the cache really through the virtual memory manager. And that is a non-trivial amount of time in terms of CPU time. So your CPU instructions, if you have a CPU, let's use easy numbers here, if CPU that runs at 1 gigahertz, okay, it probably is not 1 gigahertz, probably more, but if it runs at 1 gigahertz, giga is a billion. That means that CPU, without doing any special multitasking or anything, can do 1 billion operations per second. That's the hertz thing, okay? So without anything special, that's typically what it means. So you can just imagine now, okay, if I can do 1 billion ads per second, okay, that's like nanoseconds. Okay, well, when you go and request access to memory that's not in your caches, that's many times, that's orders of magnitude slower. So the CPU winds up having to wait for the memory to be obtained. So it's in the cache and then it'll do stuff. So what happens when you use memory in your program, if you just randomly use memory all the time, all over the place, your program will take longer than if you access memory sequentially. So if you have a big array and you go 1, 2, 3, 4, 5, you're accessing all the elements like in that order, 1, 2, 3, 4, 5, nicely sequentially going up or sequentially going down, you're going to get really the best memory performances you're going to get with the computer, because the CPU can see, oh, you're going 1 up each time. I mean, it's not very smart, but it can see 1 up each time. So I will prefetch more memory. Okay, so that actually happens. So this is what all this stuff is for. When you have to fetch more memory because it's not in the cache, those are page faults. If you get too many of them in your program, then it slows things down. Okay, so if this number is small, good. But if you have way too many of them in your code, this number will be large and you're going to spend a fair bit of waiting. Now let's go down here, because perf will output some stuff in red. If it's in red, maybe you got to deal with it. If it's not in red, you probably don't have to deal with it. Okay, it doesn't mean it's a problem if it's in red. It just means it's maybe something you got to look at. So LLC load misses. What's a load? A load is like assigning a variable. Okay, you have a value and you want to put it somewhere in memory. That's a load. Okay, sorry, that's a store. A load is getting a value from memory, and a store is the opposite. Okay, you're storing the value to memory. Okay, well, typically memory can slow down your program if you access things all over the place and crazy. Okay, so you want to know about misses. And if you're missing loads, that means your CPU, when you've read stuff about your CPU and says, hey, the CPU has the ability to predict what things I might need next. It's called pipelining, things like this. Well, if you see in the perf output misses, branch misses, load misses, okay? Anytime you see misses, it means those predictions were wrong. And there will always be misses. They'll never be zero, okay? But if you get too many of them, then it's a problem, okay? So here, L1 and LLC stuff are your caches, okay? So you can see, okay, 70% of the time, I'm missing my cache. It's probably not good. Maybe I need to look at memory use in my program. Maybe I won't be able to change my program at all, but maybe I need to look at it. Okay, now just to point out here, ITLB, the I bit, what you want to kind of focus on, that means instruction cache. Okay, and that's, if you're compiling your code with the compiler and you're not doing any assembler on your own, I would say ignore it, because you're not going to do much about it unless you can tweak your assembler. Okay, if you change the order of things in your code, you might be able to, but most tools like this spit things out in terms of assembler, and the lines of code don't mean much. If you want a better tool, then you want to explore using vTune from Intel, and that will give you some suggestions with respect to non-assembler code. I'll put it that way. But even then, it's not as ideal. Okay, but you can see here we're missing on the instruction cache too, and maybe potentially so, but don't lose sleep over this. Okay, pay more attention to the memory misses. The 2 points I want to really point out is anything to do with the cache memory hits. Pay attention to. If you see something in red, then maybe you got to deal with your program in a different way. And the other thing you want to pay attention to is branch. People say, what's a branch? A branch is an if statement. Anytime something that's equivalent to an if statement or an if statement in your code, that involves a branch. Okay, that's what the computer doesn't like when it tries to predict what your code does, because an if statement means it goes in two directions if you have two cases, right? If you have more than that, then it goes in many directions. And each time it goes in two directions, there's twice as much work to look at if you're trying to predict where things run. So what you want to avoid is branch missings getting too high. And as you can see here, it's not in red, and it's a very small percentage of all the branches. And you can see there's a large number of branches done here, but the computer was able to predict them. So we're almost out of time here. So I'm going to wrap up by saying at this point, we'll have to have a part 2 of this talk, but branches are if statements. And if you run this and you see this in red, okay, branch misses is in red. So you do perf stats and you see it in red. What does that mean? Okay, that means the computer is not able to predict the result of your if statements, and therefore you're getting less performance. So this is true, even if your program doesn't have any parallelism or whatever in it, you can run this and get an idea of that. But if this number is small, and especially if it's not colored at all, then you probably don't need to worry about branch misses. And you can tell here, wow, 2.2 billion versus 4 million. Yeah, I don't have to worry about it. This is pretty good. Okay. The other thing you might need to worry about are your cache items. Okay. By the way, perf is way more powerful than this, but you cache items. And if you see something in red, then you'll have to do something about it. Okay, great. Quick aside, I'll just point out, one thing nice perf does is it tells you what speed your program ran at. So if you are comparing between different computers, how long it took to run, if you ran perf on one and perf on the other, you can take into account, because you know how long it took in time, but you can take into account what gigahertz it was actually running. And for some of you, if you're relying on SIMD, instruction vectorization stuff, then the instructions thing is useful, and you can see how much SIMD you got because it'll tell you how many instructions per cycle. Okay, now before I wrap up with this, you can run perf with more options. Okay, this was perf stat. And what's really nice about perf stat is it spits out information like this on whatever command you're running. Now, I'll just show you. Let's do it on ls. You can even use it on a running program, which I won't show here, but you can do it. But here on ls, now it ran really fast. Okay, it ran in 4.5 milliseconds. Okay, the total wall clock time a little bit more, but whatever, it's really fast. Okay. But branch misses and all this, well, if it runs really fast, the numbers are going to be more meaningless because these are tiny numbers. But if you run it on something long running, then you're good. The other thing you can do is, let's take this A dot out. If you go -R3, okay, it will run it 3 times collecting data. Okay, so it's the second time, now it's the third time. And when it spits out the data, you'll have more meaningful data. So if it doesn't take too long to run, you can run it multiple times and it'll output all the numbers plus or minus. Okay, and your times plus or minus. So it'll give you more confidence on how long it takes to run. And these numbers will start becoming more meaningful because they're averaged over a number of runs. Well, I'm out of time, so I'll wrap up here. I'll allow for questions, and we'll have to do another thing about collecting the stats and rendering them, looking at how the program runs on multiple CPUs and all of these wonderful things.